Welcome to Spring LIB.
So we have a skier who is starting from rest and slides down a frictionless incline. So we have a skier here, and it says the angle here, let's assume to be theta here, which is 13, and the skier is sliding down. It says how fast is the skier going when she reaches the bottom here. She starts from rest here. Now, this problem can be solved by the Newtonian mechanics, but we'll use the energy approach for solving this problem. The forces acting on the skier at this point are the normal force, the force of gravity, are the only two forces, which is mg, and there is no friction. It says a frictionless incline. Now, I will write out the generalized work energy principle for using the conservation of energy. Now, whenever we approach a problem of conservation of energy, the first thing we need to do is we need to select a system. So I'll draw a boundary around the system, and our system is consisting of the person and as well as the earth here. And in this zone somewhere we have the external effects, if any. So right now, since we have assumed earth as a part of our system, so the F external or external forces are doing no work on our system. The normal force is perpendicular to the direction of motion of the object. As you can see that the angle between the normal force and displacement is 90, and the work done is FD cosine theta, and since cos 90 is 0, therefore the work done by normal force is 0. So in fact, the external forces are 0 on the system, and we'll not include gravity as such here to do work on a system, because the gravity we have taken as a part of our system. So I'll write down the generalized work energy principle, which states that the sum of the initial energies of the system. So we have the initial energy of the system, we write kinetic energy plus the gravitational potential energy plus the external work done on the system is equals to the final kinetic energy plus the final gravitational potential energy plus some internal energy, which I'll call UINT. Now in this scenario, the work done by the external forces is 0, and there is no internal energy due to friction because it's a frictionless surface. So we have a simple equation: kinetic energy initial plus gravitational potential energy equals kinetic energy final plus gravitational potential energy. So we just put the values of kinetic energy here. So we get half mv1 squared plus mg y1, assuming that this distance is y1 and the velocity here is v1 and the velocity here is v2. So this is y1 is equals to half m v2 squared plus mg y2. So we have this is 0. So we have 0 plus mg y1 is equals to half m v2 squared, and as the object reaches the bottom of the incline, the height becomes 0 here. So therefore the potential energy is 0. So if you solve this equation, we simply get v2 is equals to square root of 2g y1, and by plugging in the values in the equation, we get square root of 2 times 9.8 times 125 meters, as it is given in the problem, is the initial height. So if you solve that, you will get 49 meters per second, which is equivalent to around 110 miles per hour.